Hello and welcome to NCC Group's Cryptopals guided tour. My name is Eli, I'll be your guide. In this video we'll be looking at Challenge 10 from Set 2, which deals with the CBC mode of block cipher operation. This is a mode which historically has been very popular, but which has some notable flaws that we'll look at in a moment here. This challenge is not really about breaking crypto, it's about building something that we're going to be breaking later on. And for now, our goal is to get it working, and to make sure we understand it well enough to understand the attacks against it. So in that spirit, before writing any code here, let's pause for a bit and discuss some of the ideas behind CBC mode. Well, first off, CBC stands for cipher block chaining, and we'll see where that name comes from in a moment. It's a common mode of operation for block ciphers. You'll often see a CBC out in the wild. And when you do see it, more often than not, it indicates a system that should be looked at more closely. The reason being that while CBC mode is still popular, at this point, it's mostly popular with amateur cryptographers, armchair cryptographers, while the rest of us generally agree that while CBC mode is not necessarily bad per se, it is not ideal either, and most of us would not choose to include it in new designs in 2022. We'll see some of the reasons for that momentarily, but first let's start with the definition of CBC mode. Our starting point for this diagram will be something we've already seen, which is ECB mode encryption. To go from this to CBC mode encryption, we need to just make a few small changes. We'll start by taking this first ciphertext block and XORing it into the next plaintext block. This is the eponymous chaining step, and its goal is to scramble each plaintext block before encrypting it. And then, of course, for the first plaintext block, we have no previous ciphertext block to use, so we're going to need to invent a new block of random bytes. This block is, of course, the famous initialization vector, or IV. This block does not need to be secret, but it does need to appear random to an attacker. And it is technically distinct from the ciphertext, but in practice we usually prepend it to the ciphertext and treat them as one and the same. This diagram here is the most common way of drawing CBC mode. It's what you'll usually see in textbooks or papers. But you could also draw it like this, where the chaining proceeds vertically, which, if you ask me, it looks quite nice. We could also illustrate it in terms of a buffer being encrypted in place. In real life, typically encryption doesn't happen in place. It's more common for the plaintext and ciphertext to occupy separate buffers. But some APIs do allow for this, and more importantly, I'm hoping that seeing things this way will help with building intuition for CBC mode. Now, having already alluded to the motivation for this construction, let's talk about it in detail. Why is CBC designed this way? Why do we need an IV? Is this chaining step necessary? What's the motivation for all this? Well, let's start with the IV. Note that there is a degenerate case here. If the IV is all zero, then the XOR will be a no-op, and then we're effectively back to ECB mode, at least for this first block. In this case, we have all the issues that we had with ECB. For instance, consecutive encryptions of the same plaintext block will always result in the same ciphertext block. And more generally, this problem exists with any fixed or reused IV, not just for the zero IV, which is why each ciphertext's IV needs to be randomly generated. And indeed, we can see here that if we modify this figure to use properly randomly generated IVs, then that change propagates through the XORs and is reflected in the ciphertexts. And now we see what we want to see, which is that two consecutive encryptions of the same plaintext block have resulted in two completely different ciphertext blocks. This is what we get by using an IV. So now we've motivated the use of a random IV. We could generate an IV for each block of plaintext, but this would be massive overkill. It would double the size of our ciphertexts. We can do better than this. Recall that our IV does not need to be secret, it just needs to be unpredictable to an outside observer, or in other words, to appear random. There is a related property called indistinguishability, which all good ciphers are expected to have, by which we mean roughly that ciphertexts should appear indistinguishable from random bytes. Really, there's a bit more to it than that, but that'll do for this discussion. And it follows from this property that if we just need our IVs to look random, then ciphertext blocks could be used as IVs. And this gives us a sort of inductive step by which everything that we've just said about IVs can be applied to this chaining step as well. But now that we've covered the why and the how of CBC mode, I want to take you on a quick detour to show you a variant of CBC mode that is uncommon but kind of interesting. This variant, which I alluded to back in Challenge 9, is called CTS mode, which stands for ciphertext stealing. You can also read it as a bit of a pun on counter mode, because S is the letter following R. I have to assume that was intentional. And what's interesting about CTS mode is that it works very similarly to CBC mode, but with a little bit of a cool trick at the end that allows it to get around the need for padding entirely. CTS mode starts out just like CBC mode, the only differences are in the last two blocks. So after computing this far just as we would in CBC mode, we're now going to take a number of bytes from the penultimate ciphertext block equal to the length of the final partial plaintext block, and we'll move these out here to the end to create a partial final ciphertext block. Next, we're going to XOR the final plaintext bytes into the penultimate ciphertext block, and to keep those bytes secret, we'll re-encrypt this whole penultimate block. This gives us our final CTS ciphertext, although I should caveat that by saying that there are technically 3 variants of CTS which differ in how they order these final 2 blocks. And if you're sitting there wondering how it's even possible to have 3 different ways of ordering 2 blocks, then I encourage you to look this up on Wikipedia and see for yourself because it's really remarkable. All that being said, the ordering shown here is, in my opinion, the only good one, so it's the only one we'll cover. To decrypt this ciphertext, we need to handle the final 2 blocks differently as well. We'll start by decrypting the modified penultimate block, which allows us to recover the final plaintext bytes, after which we can reconstruct the original penultimate block, which we decrypt again, and from that point onwards, decryption proceeds as normal for CBC mode. So we see that CTS uses the same number of calls to the cipher as with CBC mode. It just encrypts parts of the buffer twice. The main difference here is that we end up with a ciphertext that is exactly as long as the plaintext, and of course, we also get rid of the possibility of padding errors by getting rid of the padding. So that was how it's performed in place. Here's how that process works with separate plaintext and ciphertext buffers. We'll zero pad the plaintext so that we can XOR it against a full ciphertext block. We'll encrypt the penultimate block, put that in the final position, and truncate it. We'll take that same full encrypted block, non-truncated, and XOR it against the zero-padded plaintext, then encrypt the result and store it as the penultimate ciphertext block, and there you have it, that's CTS. If you're still confused, well, don't worry, because this never actually shows up in the actual Cryptopals challenges. That said, it does sometimes show up in real life, and more importantly, I think it's interesting. And after all, what's a guided tour without some sightseeing? Now let's wrap up this discussion by looking at some of the limitations of CBC mode. We will see a few attacks on CBC mode in the challenges to come. Those attacks all focus on what happens when you misuse it in some way. For now, we'll focus on what happens when CBC is used correctly, because it turns out that even under ideal conditions, CBC mode still has some shortcomings that are worth knowing about. The first downside is performance. Note that each ciphertext block's computation depends on the previous ciphertext block. This means that the ciphertext blocks have to be computed in series, and as a result, this mode of operation cannot be parallelized for encryption. We see this illustrated here. In order to compute the final highlighted block, each previous highlighted block must be computed first. This is a clear-cut disadvantage of CBC relative to modes that can be parallelized, like counter mode. But to be fair, like I mentioned, for CBC this drawback only applies to encryption. Decryption can be random access, and it can be parallelized, because while it does have the same data dependency that encryption has between adjacent ciphertext blocks, in this case each ciphertext block's value is known, and they don't have to be computed to be used. So that's one downside, and it is a real one, but it doesn't really have to do with CBC's security margins. This next problem does, though. Let's start by recalling the IV discussion from earlier. It's worth noting, and this is sort of a subtle point, that even in this fixed version of the system with random IVs, there is still a tiny amount of information being leaked here. Let me show you what I mean. Suppose that the inputs to these XORs were such that their outputs were equal. We'll achieve this by setting the plain texts equal to the IVs, so that their XORs will null out, although that's not the only case where this can happen. Now in this case, the ciphertexts would again be equal, as we can see here, even though the IVs and messages are both different. Let's put this in algebraic terms. By checking whether the ciphertext blocks are equal, we're able to test whether the first plaintext XOR the first IV equals the second plaintext XOR the second IV. Now let's do some algebra. These IVs are publicly known values, so let's put them together by themselves on the right-hand side. And now the values on the left-hand side of this equality are secret, but the values on the right-hand side are not. So this is an information leak. Of course, this equality holds if and only if the ciphertexts are equal. If the ciphertexts are not equal, then all we learn is that these XORs are not equal either. But that is still an information leak because it gives us an impossible value for the differential between these two blocks. So how bad is this? Well, it's not nothing, but it's not usually a showstopper, because if the IVs are randomly generated as they're needed, then the value of this differential should be evenly distributed, and just as importantly, they should be unpredictable, which does a lot to make this property less exploitable in practice. That said, if IVs are not properly generated, then things get worse very quickly. For example, if the IVs are equal, which would happen if an IV is static, or if it just gets generated and then reused, then this right-hand side simplifies to 0, and we can rewrite this as a non-equality between the plaintext blocks, or as an equality as the case may be. Note that this is particularly bad in the case of a chosen plaintext attack. Suppose, for example, as an attacker you control the first plaintext, and you want to learn the contents of the second one. You might have some guesses for what it might be. Well, with the right setup, this property would allow you to test each one of those guesses and thereby potentially learn the contents of the unknown block, which is, of course, very problematic. So to summarize, the amount of information leaked here is non-zero, but when CBC is used properly, the leak is very small and hard to exploit. And so there you have it. And there is, of course, a whole lot more that could be said about CBC mode, and we'll come back to it a few times. But for now, let's leave it there, and let's write some code. Alright, so for this section of the video, our goal is going to be to get this file decrypted. We take a look, we see that it is currently base 64 encoded, and this is a base 64 encoded ciphertext. So if we were to decode this, we would have a pretty hard time reading it without getting CBC mode working. We're going to go ahead and implement it by hand. I'm going to skip implementing encryption for now because we don't actually need encryption in order to decrypt this. And you can see that we already have this file downloaded. So let's get started on the challenge. Now everything here is going to be bytes, conveniently enough. We're going to go ahead and take in a user-specified IV. We're not going to assume that the IV is prepended to the ciphertext or anything like that. We're going to take it as a separate field. And the first thing that we're going to want to do is break our ciphertext up into blocks, which we're going to need our bytes to chunks function for from challenge 8. And you recall this is a fairly simple function that just breaks up a byte string into chunks, which may or may not be blocks, but in our case they will be. And rather than using 16 as a magic number here, let's go ahead and define a global block size variable. Now recall that the chaining step uses the IV and the previous ciphertext more or less interchangeably. So for most of our chaining steps, we're going to be chaining in a previous ciphertext, and we're just going to pretend that our IV is our 0th ciphertext. And that is precisely in line with the challenge description here. We're going to say previous ciphertext equals IV. That's its initial value. And we're going to start with an empty plain text, and we're going to build it up one block at a time. And this needs to be the result of an AES decryption. And so let's go ahead and import our decryption function. And this, of course, good lord, that's a long type signature. This is just a wrapper around PyCryptoDome's AES. And this, as it happens, actually has its own block size constant. So let's go ahead and just pull that in here too. And now that's even more explicit. And we're going to decrypt this block using the provided key. Then we're going to take that value and XOR it against the previous ciphertext block, because this is how we decrypt in CBC mode. And for bytes XOR, where was that from? Challenge 2. And now, of course, we're going to update our previous ciphertext variable to hold the block that we just looked at, which is going to be a ciphertext block. Now, at the end of this loop, we will have the full plain text. It will be padded, but yeah, I wonder if we should be removing that here or if we should leave that up to the caller, right? I don't know, I could go either way on it. I think for now, let's just return it. Well, no, I don't think that's the right thing to do. All right, so now we have a parameter. If PKCS7 is in use, then we will, strip it here. Otherwise, we're going to leave it to the caller to handle the padding. Another way we could write this is to accept an unpad function. And then if you didn't want unpadding, you could just pass in the identity function there. But I think that's a little bit overwrought for this use case because in the real world, in any sane circumstance, we're going to be using PKCS7 anyway. So let's just make that simple. Anyway, so now we're going to pull in the base 64 data and we're going to decode it. Now we could write this like this, but personally, when we're using null bytes, I prefer to write it like this. And let's talk through what we've done here. We have a main guard. We are decoding the ciphertext, and we're using the provided values for the key and the IV. This is the key, and this is the IV. And then we're just calling... Well, yeah, I suppose we don't need to strip PKCS7 if we're already doing that in here. Isn't that right? So we're just going to call this with this argument at its default value, and then we're going to print the results. So let's see if all goes as expected. And there it is. This is, of course, only somewhat intelligible, but we can see the plain text starts. I'm back, and I'm ringing the bell. A rockin' on the mic while the fly girls yell. An ecstasy to the back of me. Well, that's my DJ Deshay cutting all them Z's. And I would go on, but I think you get the idea. Anyway, that's challenge 10. I hope that you found this helpful, maybe learned something, and I'll see you in the next one.